All right, so with that, I think we can go ahead and get started so that we don't go long. So my name is Nathan Pacini. I'm the marketing manager at Data Science Dojo, and with me today I have, and again, apologies, Wojtek Kuberski. He is the founder of, and I have the wrong tab open. There it is. He is the co-founder of NannyML, and which is a startup monitoring machine learning models in production. And he is going to be giving us a talk on how to detect silent failures in ML models. This will be kind of a two-part presentation. The first part is going to be kind of slides and more presentation-like, and then we'll stop for Q&A there, and then we'll do a tutorial, and we'll share the what is the we'll share the docs and the GitHub repo as well with you at that point, and then we can go ahead and we'll do a demo, and then we'll stop for Q&A at the end of the demo as well. So Wojtek, why don't you go ahead and take it away? And again, for questions, please use that Q&A tab. If you're on live stream, we'll pull your questions into Zoom for you. And now Wojtek, sorry. Now you can go ahead and get going, and I'll shut up here.
Yeah, thanks a lot, Nathan. So let's get started. So as Nathan already mentioned, today we're going to talk about detecting silent machine learning failure in models. And we're going to be mostly talking about the models that are already deployed to production. So you created them, you iterated on them, you decided that they're good enough, and you decide, let's deploy them in production. They are successfully deployed, they operate in production. And we want to see how we can see whether these models are actually working correctly or not, what happens if they fail, how to detect it, and how to resolve it. So you can treat it as kind of an introduction to machine learning monitoring. And with that, let's get started with the agenda. So the first point on our agenda is data-driven concept. These are two main reasons why machine learning models can fail in production. We're going to define them. We're going to see what are they, how we can kind of build an intuition of how they might happen. We're going to define them more formally, and we're going to start talking about how they can actually impact your performance. So by performance, I mean, technical metrics like ROC AUC or precision. And then we're going to go from that to the second point, which is the performance. And we're going to talk first about why we can simply calculate the performance of our models like we would like to in most cases, and we need to estimate it instead. Then we're going to delve deeper into the algorithm that we developed, which is, as far as we know, the only algorithm available right now to wide audience that can estimate performance of an algorithm, of a machine learning model without having access to ground truth or to targets. So we're going to develop intuition of how this algorithm works. And then once we learn how to detect changes in performance, deterioration of performance, and in extreme cases, model failure, we're going to go back to data and concept drift to kind of troubleshoot and figure out what exactly went wrong and how we can fix it so our models are performing well again. And just before we jump into the first part of our agenda, let's set the stage with a typical use case that you might really want to monitor. And this use case is going to be loan default prediction. So we're going to be talking about taking credit scores, customer information, and we'll try to predict whether a given customer is going to default on a loan that we intend to give them. And the target here is going to be a non-payment within 1 year. So that means that we'll have to wait an entire year before we know whether our predictions were correct or not. And to measure the performance of our machine learning algorithm, here we're going to be using a technical metric such as ROC AUC, which is a very typical metric for evaluating binary classification models like this use case here. And I'm going to be referring to this use case throughout the presentation, just to give you a bit more, grounded and specific examples of how, for example, data drift can impact performance. So let's get started, and let's talk about data drift and concept drift. So to kind of give you a high-level intuition, we're going to start with what are we actually trying to do when we develop a machine learning model. So what are the kind of core components here? The first component is the true pattern that exists in the world. You could see it here with an example that there's going to be feature X, and there is some kind of binary variable, which can be either positive or negative. And we see as X increases, the chance that a given point is going to belong to a negative class also increases in kind of the sigmoidal fashion. Then the next thing we have is our sampling mechanism, so how we gather the data. So this can be basically any distribution. And then what we end up with is the data that we're going to use to develop our machine learning model. So maybe we'll split this data, in training, validation, testing. Maybe we'll do some cross-validation there. This is the data we have access to, and it's going to have some kind of, target distribution depending on feature X here. So we have that, and we develop our model. And now what can change? Both the true pattern and the sampling can change. So now let's investigate what happens if the sampling mechanism changes. So if sampling mechanism changes, we have data drift. So the true pattern that we're trying to kind of find or approximate with our machine learning model is still the same. Nothing has changed there. What has changed is really how we sample from this pattern, this population or even meta population, into what we actually have access to. So maybe, in 1 month, we're sampling like you see in the original sample, and in another month, we're sampling slightly more to the right. Maybe because the X is actually the age and people are getting older in developed societies. So we will see that there is slight data drift every month or every year towards a slightly older population, or maybe a given region is getting more affluent, more wealthy, and we see that average income goes up. So the value of this feature will slightly drift to the right. And now we have this intuition of what's the difference here between data drift and, as you will see, change in true pattern is going to be concept drift. So let's define it formally. So data drift is change in the joint model input distribution. So we'll be looking at all the input features at once, and we'll try to see if this distribution has significantly changed. And you can see here that before the data drift, we have certain distribution along the x-axis, and after the drift, this distribution is different. That's simply data drift, or also known as covariance shift. But here we use data drift kind of as an umbrella term, because if this changes, that also means that the distribution of model outputs will change. But let's not delve into that deeper. Let's focus now just on the difference between data drift and the concept drift. So now, moving on to the concept drift. So here, the sampling remains the same if we have pure concept drift. What changes is this true underlying pattern that we're trying to find. And you see here that we had this kind of sigmoidal function before between the value x or feature x and our relative frequency of the targets. And we see right now it's becoming a bit less sigmoidal and maybe more straight. And that's an example of slight concept drift, which still might be very relevant and might impact the performance of the model. If we see a bigger change, so maybe instead of being positively correlated with the negative class here, if it became negatively correlated, so we'll see it from going from this way to that way, that would definitely mean that our models are not working as they are supposed to, because the pattern that they were trained to capture is no longer relevant. So data drift may impact performance. It does not always impact performance. It might impact performance if, for example, the data moves from regions where the model is performing very well to regions where the model is not performing very well. But in case of concept drift, almost always we will see a drop in performance. So again, our data on the input, from the input perspective, so the distribution of the features will look, roughly speaking, the same if there is no data drift and there is pure concept drift, but the distribution of the targets will change. So that's basically concept drift. And to, again, define it a bit more formally, the concept drift is change in the underlying concept or the pattern between the target and the model inputs. So it's the probability of the target given the features. And instead of looking at the full distributions, as we were looking before, we could also look at it from a slightly simplified perspective, and we could look at class boundaries. So imagine that these are true class boundaries between the positive and negative classes. And so this is not something that we learn, but it's something that actually exists in reality. And we are trying to, of course, learn this pattern. And on training data, we'll have the one that looks like this. It's like a curve to the right. And then in production data, we will see there is strong concept drift, and this class boundary looks completely different. So now imagine that we learn that kind of pattern and then we're trying to apply it to data that looks like that. Of course, our model is going to fail and the performance of the model is going to significantly decrease. So now we defined concept drift and data drift and how they potentially might impact performance on high level. Now, let's delve deeper into this performance. So first of all, why should we really care so much about performance? Why can't we just look at data drift and say, yeah, there's data drift, our models are not working correctly anymore? So first and foremost, because the data drift does not equal performance drop. Imagine that you have data and you have kind of three main segments in the population. You have old people with very high income, and we know that these people are not going to default. And we have young people with also very high income, and then we have, let's say, young people with low income. If the data drifts between old people with high income to young people with high income, and they are both very, very unlikely to default, the model is most likely going to perform quite well because it's very good at separating negative from positive classes there. But if we drift towards kind of the closer to the class boundary from the Williams when the model is stated, we would expect drop in performance. So whether there is drop in performance or not really depends on the details of how exactly the data drifts in relation to the pattern in the data and in relation to the uncertainty of the model and how hard the problem is in a given region to solve, how hard the classes are to separate in a given region. So that's the first reason why we cannot just look at data drift. Another one, which is kind of trivial, is that performance is something that we optimize in training. We pick our metric, let's say we pick F1 or log AUC. We pick it because it is a business impact proxy. We optimize it in training. We may be trying to optimize hyperparameters just to get this metric as high as possible. And since we did it in training, in development, we should continue to monitor this metric in production. And why is that? Because it is exactly the business impact proxy. In the end, what matters is that our models drive business impact, whether it is in dollar value or whether it is in something that does not translate directly into money. We want to drive impact. And that's why we develop models. That's why we are creating these pattern learning mechanisms. So these are simply the reasons why we want to make sure that we know about the performance of our machine learning model at all times after we deploy it. And now the simplest solution to that is to simply calculate the performance. And that would be nice if we could do it. But now let's look at our typical use case with credit scoring again, or with loan default prediction to be more specific. And we actually do not have ground truth after we deploy the model. And why is that? First of all, the data is delayed. The target data specifically is very much delayed. We need to wait an entire year to really see whether our predictions were correct or not. We could potentially try to use some kind of proxy labels as people are being late with payments, but these things are not fully reliable, not always available, and sometimes in a completely different database that we as data scientists don't have access to. So the data is delayed. That's first thing, and we just cannot access it. It's impossible to do it, and we don't want to operate a machine learning algorithm that can potentially drive billions of dollars in value for a year without knowing whether it's performing well or not. Because in these cases, because we're pricing risk in a sense, we can go from a positive risk-adjusted ROI per loan to a negative risk-adjusted ROI per loan, which means that instead of making money by giving away loans, we might be losing money with every loan, which might lead in extreme cases to 2008-like scenario when an entire bank can go bankrupt. Second reason why we don't really have the ground truth and we cannot just calculate performance is not having access to complete labels. And what do I mean by that? So imagine that we wait a year and we actually know whether a person has defaulted on the loan or not. So then we know for every person that we predicted that he's not going to default on the loan, they're not going to default on the loan. So for every instance of a negative class, we know whether it's a false positive or a true positive. So whether we are right or not about this person defaulting. But we don't know about the people who rejected. For every person that we predict positive class that the person is going to default, we will never know whether we were right or not. And there are, again, some techniques that can somehow help us here, like reject reference, but again, they're not fully reliable, and they are reasonably hard to implement and don't perform very well. So again, we have, that's the second issue, incomplete labels. And then the third issue is kind of separate here, and it's a family of use cases when instead of trying to predict something like lone default, we're trying to automate something like classifying documents into relevant or not relevant, for example. And here, what we're trying to do is essentially replace human labor with automated decision making. And that means that if we were to always get invalid ground truth, we would need humans to review the same work that the machine was developed basically to do instead of them. So that would make the entire use case useless or worse than useless. And here, as always, there's some ways to get a bit of ground truth. So we could do, for example, spot checks when we take 1% of the data, 2% of the data, and we tell people, humans, to redo it to get some kind of idea of how well the model is performing. But again, we're not covering everything here, and we don't really have ground truth for vast majority of the data points. So since we cannot calculate it, what can we do instead? We can estimate. So how do we do this? Since the entire algorithm is reasonably complex, not complex, mind you, but reasonably complex, I'll start by giving you a high-level intuition of how this thing might work. So what you see here on the left is this kind of a butterfly data set. When what you're seeing in green and red are the regions where the model that we trained is more or less confident. So on these wings of the butterfly, we see that the model is confident. This could be that the right wing is the region when there's most of the positive class, and the left it is the region when there's mostly negative class. And then we have a class boundary where the model doesn't really know whether to say positive or negative, and we'll have predictions like 0.55. That's in the middle. And what we're trying to do with this algorithm that I'll explain in a while is trying to predict or estimate the impact of data drift on performance. So we are assuming that there's no concept drift, and we're looking only at the impact that the data drift might have on performance. And imagine that the blue points are our data points in our training data set on the left and production data on the right. And in training, they are kind of spread throughout the entire space. Whereas in production, they kind of converge or drifted. So there's data drift towards the regions that are less confident. Then we can reasonably assume that since the model is less confident, these regions are actually harder to predict. So we will see that the performance of the model has decreased. And now, how can we potentially quantify this? So the first step would be to figure out whether the model is correct or not with its confidence estimations. And the way to do it is so-called probability calibration. So what you normally get out of a model when you do predict proba in scikit-learn is a number between 0 and 1 in binary classification. And this number actually normally does not represent probability. We need to calibrate it to make sure that if it says 0.7, there's actually 70% chance that this model, this data point belongs to a positive class. I won't go into detail of how to do probability calibration. This is standard technique, and there is literally out of the toolbox, even in scikit-learn to do so. So let's assume that our probabilities are properly calibrated. And by the way, in NumML, this is already done behind the scenes, so your models do not need to be well calibrated. You just need to input predictions as they are, and they will be calibrated behind the scenes. So we have well-calibrated probabilities. In other words, that means that if a prediction says 0.7 or 0.3, that means that is exactly the probability that a given point belongs to positive class. Now we know that. What else do we know? We know the threshold that we will use as a business rule to make our prediction. So let's say that this threshold is 0.5. If a prediction is above 0.5, we're going to classify a given point as positive. If the prediction is below 0.5, we're going to classify it as negative. Just an example, right? We have to pick it at some point to make a business decision. Let's say we pick 0.5. Then we're going to take every single point in our production data set point by point. And we're going to say whether it's going to be a positive or negative prediction. And we know for a fact whether it's going to be positive or negative, depending whether it's above or below the threshold. And then we will look at the value of this point. And that will tell us, again, for a fact, because we know probabilities are well calibrated, what is the chance that this is going to be a positive, a false or true prediction. So let's say that the value is 0.7, or let's stick to 0.7. Then we know that it is going to be a positive prediction, and we know it has 30% chance of being a false positive and 70% chance of being a true positive. So what we're going to do is we're going to construct now a confusion matrix, a partial confusion matrix that only has one point in it. And we're going to assign 0.3 to false positive cell and 0.7 to a true positive cell. And we're going to do it for our entire data set in question, so our entire analysis data set. It can be last week, last day, last hour, last month, last 10,000 data points, whatever you're really interested in from kind of business perspective. And of course, we need to make sure that this data set is big enough so we have a representative sample and we're not just trying to capture, small random changes in performance. And we're going to create this partial confusion matrix for every single point in the data set. And then we're going to just sum them. What we end up with is we end up with expected confusion matrix of the algorithm for classification purposes for a given range of data according to the model itself. That's the model estimating its own performance via this algorithm. And then we can take this expected confusion matrix, which as long as there is no concept drift and there is only data drift, is actually the true expected value of a model for a given data set. This might not be exactly the same as the observed value, because it might be that even though there is 70% chance that a given point is negative, or sorry, positive, and there are 3 points similar like that in a data set, 2 of them turned out to be negative, just due to sampling. So we might observe certain small changes or deviations from this expected performance, but this algorithm gives us true expected performance of an algorithm in absence of concept drift and assuming that probabilities are well calibrated, which are two big assumptions, of course, but we can take care of the second one of probability calibration. And when it comes to concept drift, it's something that we're currently working on. So we know how this algorithm works, and in our tutorial part of the presentation, we're gonna actually implement it with the help of NanoML on an example data set. So we'll see how this actually looks like in practice. Now, let's look at the second part of the presentation that has to do, third part of the agenda, which has to do with detecting data drift. So we try to figure out and troubleshoot what exactly went wrong and why our performance has decreased. So here, we have two ways of detecting data drift, roughly speaking. So the first one, when we look at every feature, so every input feature separately, and we're gonna see whether the distribution of this feature between our reference data set, which can be, for example, our test data set for which we know everything is fine, and our analysis data set, so the part that we're trying to analyze, has changed. And for that, we can use very simple statistical tests such as KS test for continuous data or chi-square test for categorical data to see whether there is a significant difference in distribution. These things are very simple, very easy to interpret, very fast to run, but they have two very significant downsides. The first one is false positives. So imagine that you have 100 features in your dataset, and that can easily happen in basically any use case. Then you will constantly see small changes that are statistically significant basically everywhere. And that does not mean that the performance of your model has decreased, because again, data drift does not equal performance, but you will not be able to really figure out what's going on and will literally drown in alerts. This is like one of the easiest ways to do machine learning monitoring, but in some respects, even worse than not doing it at all, because you just get 100 alerts every time you run it, and you're like, yeah, okay, there's just no way to really go through it manually and see which of those makes sense, which of it doesn't. Another big downside of doing it feature by feature, so in a univariate way, is that it assumes that these features are in a way independent, and it does not look at data drift that has to do with relationship between features. Imagine that the correlation between two features actually changes, and one of the strongest discovered features of a model is one feature times the other. In that case, of course, we can see that the performance of the model might change, but it's not going to be captured by our univariate data-driven detection. So we have both the false positive issue and the false negative, because we will not be able to find complex data drift and complex changes in the data structure. So to do those, we'll have to sacrifice interpretability a bit, but just a bit, and we'll look at multivariate data drift detection. And I'm going to describe an approach called data reconstruction, which we developed again at NanoML, which is quite novel as well. And I'm going to describe how it works and how we can use it to really detect data drift that captures basically any change in the data structure between the reference and analysis data. So here, what we're going to do is we're going to take a dimensionality reductor that has some kind of inverse transform. So it can be PCA, it can be manifold learning techniques like UMAP, anything that really compresses the data or reduces the dimensionality of the data in some way, or it can be even like more powerful approaches like variation autoencoders. So we're going to take the original data and we're going to train this reductor on our reference data set. So again, it might be our, for example, test set that we use to evaluate the quality of our model. Then this algorithm is going to learn the internal structure of the data. Imagine using VAE. So it will learn all kinds of, patterns there. It's going to learn to compress the data with minimum loss. And then we're going to see how the reconstructed data differs from the original data. So we're going to train it or fit it on the reference data, and then we're going to transform both the original data and the analysis data, and then we're going to do the inverse transform also on both of those. And we're going to measure the difference between the original and reconstructed data. And from there, what we're going to get is we're going to get a reconstruction error. And we're going to have it for our reference period and all the analysis periods in question. So this is basically the graph here on the left. And you see that this reconstruction error is basically a way to measure dislocation of points before and after the reconstruction. So it can be any distance metric here. What we're using is the simplest possible one, which is just mean Euclidean distance between the original and the reconstructed point in the original space. And if we see that this reconstruction error stays roughly the same, so the compression loss, you could also get compression loss, stays roughly the same, we don't expect to really see the data drift, because the learned data structure, the data structure that was learned by this compressor, is still equally relevant to the data as it was before. If we see a drop in reconstruction error, then funnily enough, we do expect data drift. We can interpret that as data drift because it means that this learned structure is now resembles the real data structure more. So the data maybe became simpler or just looks more like what we learned, and the loss is lower. And of course, if the reconstruction error increases over time, it means that this learned internal representation of the data is no longer relevant or not as relevant as it used to be. And we see that there is data drift. And just to mention here, there are a few requirements for this compressor. First of all, of course, the encoding needs to learn the internal structure of the data. It also needs to reduce the dimensionality of the data in order to really force this compression. We need to be able to do inverse transformation just to measure this reconstruction error or the compression loss. And last, slightly less obvious requirement is that the latent structure needs to map in a stable way to the original space. And this is really the most important requirement here. And there's lots of methods that don't meet it. For example, simple autoencoders don't really map in a stable way between the original and the latent space. So small change in the latent space can lead to a huge change in the original space when you reconstruct it. That means that our reconstruction error will not really be meaningful, and we wouldn't be able to use it to measure the magnitude of data drift. And just to give you a quick example to continue building the intuition behind it, let's say that we use our PCA for our drift detection here, multivariate drift detection of data reconstruction. And we see two data sets. The data set in orange is the reference data set, and the data set in blue is the analysis data set. And if you look at it per feature, so along the x-axis and along the y-axis, your KS test will basically tell you everything's fine, there's no changes in distributions. Because if you look at it from 1D perspective, there is no change in distribution. The distribution is equal in both cases. And if we use our reconstruction error method, we will see that there is a huge change in the reconstruction error because, of course, these data sets are very, very different. And that is really it. So now let's just quickly summarize. First important thing is data drift and concept drift are two most important causes, underlying causes for drop in performance and potentially machine learning failure. And while concept drift generally does tend to lead to drop in performance, data drift does not always lead to drop in performance. Then we would love to we should always know the performance of our models, but in most cases, production targets are not available partially or fully to calculate performance. So we need to estimate the performance, and this performance estimation is really the key to machine learning monitoring. And only from there, we should go back to data drift and try to figure out what exactly happened and try to troubleshoot and resolve the issues. So again, thanks for listening. And this is the end of the first part of the presentation. Check out our GitHub, our website. Feel free to add me on LinkedIn if you want to ask some questions later on. And now let's have a few rounds of questions from the audience.
Yeah, so if you have any questions right now, start typing those out. I know my team is going to be sharing some of the links, including the GitHub link that Avoiditech here is sharing with you now. So first question is from Tarek, and I should say first question and so far only question because I'm not seeing any other ones at the moment. Is from Tarek, and Tarek is asking, can nanny ML be used to estimate the performance for healthcare models? Examples being image classification, segmentation, or object detection.
Okay, so when it comes to healthcare models in general, absolutely yes. Your examples are only from the domain of computer vision. Funnily enough, so assuming that you mean specifically computer vision models, it's something that we don't focus on currently, but you should absolutely be able to use NannyML for it, as long as you make sure that you convert the data into tabular format, which actually happens, basically if you convert it to anything that can be understood by a neural network. So RGB plus alpha channel, if you put it in this format, it's basically tabular, and NannyML should be able to detect data drift, concept drift, change in performance. Of course, bear in mind that the interpretable kind of data drift, which is the univariate one, will really return gibberish because it will just tell you that there's more red, which doesn't really make more sense. But when it comes to the performance estimation part of NannyML, definitely you can and you should use NannyML for it.
And then this one I think is from one of our live streams. This is from Sanket. What's the best way to score the model?
Okay, so that's a very loaded question, and the answer is going to be very disappointing. It depends. So basically, You should score the model, or you should evaluate the model in a way that matches the business impact the best. So if you can quantify expected business impact of the model in some way, you should try to turn it into metric. And then you should either pick a metric that corresponds to that, or try to come up with a new metric that corresponds to that, or pick one of the existing metric that's a close proxy to it. So maybe it's about document classification, and you know that every time that somebody basically does a false positive, it costs you $10. If it's a false negative, it's $1. Then you can do F beta score with beta equal 10 or 1/10, and that's your metric. So you should always start with the business perspective in mind, and from there try to create a metric that corresponds with it as best as possible.
And then not really a question for you, but a question for me was there was a question about recordings and where to access recordings and everything. Because we do record each of these and we post them on our website as well as our YouTube channel. So I think Medha, you were the person that asked that. And then Fatima, if you can share the link to our YouTube channel as well as the online.datasciencedojo website. Those are the two places where we'll post the videos. And then we also have a LinkedIn group that Fatima and the rest of our team will post the videos in. So you could either join the LinkedIn group and just wait for notifications for new videos to drop, or subscribe to us on YouTube, or just visit our website. And that's where the videos are. So hopefully that helps clear everything up. Okay, so I think we're done with Q&A at this point. Do you want to go ahead and oh,
absolutely.
Never mind that. Hold on, there is one more question. Maybe. Okay, so can you please explain a bit on model retraining approach, i.e. the continual learning process?
Yeah, so there's kind of two slightly different things here. One of them is so-called continual learning or online learning, when we are basically continually training our model as new data points come in. And that's a very interesting kind of use case, which is, as far as I know, not yet very popular in industry because of engineering challenges. But if you can do it, you should absolutely monitor your models, because what you can see is maybe there is some kind of feedback loop where the model actually changes the population. Imagine cart abandonment use case, right? So we're trying to predict whether somebody is going to abandon their carts and what is the chance that they would actually complete transaction, let's say on Amazon. And then people actually learn, especially in the US by now, that if they on purpose don't check out for 2-3 hours, they're almost guaranteed to get 10-20% discount. So here the model itself changes the characteristics of the population. And you will see that the model itself is actually going to start to perform worse because it itself is acting on the population. Mm-hmm. And that is just model acting one way. Now imagine that you are in online training regimen when you're also retraining everything. Then it kind of closes the loop and it creates a full feedback loop that in some ways is going to stabilize and it's going to be great, but in some ways can lead to total model failure. So absolutely, in these cases, you need to monitor your models. When it comes to retraining based on monitoring, so we're not in online learning now, but we are just retraining based on something. Basically, the idea is that if retraining is cheap, just retrain every day. If retraining is not cheap, you should look for not a data drift, but actually significant drop in performance that's persistent in time, maybe for a week, and retrain that.
Okay. And now let's go into the demo. And I know we have another question, but we can save it for after the demo.
Absolutely, cool. So now for demo/tutorial, if you want to follow with me, you can just go now to our GitHub. So we are fully open source, free library, written almost entirely, as you can see here, in Python, for Python, first and foremost. And feel free to go to our GitHub and either install an email very simply here, or just follow with me, and we'll be using our docs. So now For you to remember how to do it, we'll just go to our documentation and we're going to click on Quick Start. So first thing we need to do is we need to install NanoML. So I have here basically a fresh Anaconda Python 3.8 environment, and I already actually installed NanoML, but we're gonna install it again just in case. And of course, this is not gonna work. How do I install things in? No. So let's skip the installation here, and let's assume you install it through a command line through your Anaconda prompt. So you take Anaconda prompt, go pip install, and you have NanoML installed. Then the next thing is we're going to import pandas, because you always import pandas. We're going to import NanoML as well. So we're just gonna import things, and things are imported. Now, as an example, we're going to load our synthetic dataset. It's a dataset with binary classification that is kind of based on what can happen in the real world. So we're loading our synthetic data, and we see here that it's data about whether somebody is working from home or not. So based on kind of whether somebody has worked from home and some characteristics of the population and the environment, whether a person is going to work from home or not, which might, for example, influence salaries in some companies. So we see just examples of our reference data set and analysis data set. Now let's continue. And what we'll have to do here is we're going to choose what is the size of our chunk. So chunk is a concept in NanoML of what is the kind of sample size that you want to see in time as you move forward in time. So maybe you want to look at 100 data points at once or 5,000 data points at once. And the idea here is the higher the chunk size, the more stable the results. But of course, we need to have more data to really see evolution in time. So here we're going to choose 5,000, which is generally a safe chunk size when we know that our estimations will be quite trustworthy. Then what we're going to do is we're going to try to estimate the performance of our model. So here we'll have to feed an estimator. And again, I'm just going to copy it and walk you through the code as it is here. So what we're doing here is we feed an estimator, which is our confidence-based performance estimation algorithm, which is the one I explained in the presentation. And we need to know what is the column for y per proba. So what is our kind of column that tells you what is the probability? What is our column that has model predictions? What is our column that has the target? And the target does only need to be available in our reference. We don't need the target in our analysis. As I mentioned, we're trying to estimate performance without having access to targets. Since everything is really temporal, and we're looking at things as they change in time, data that happens in time, or we also need some kind of timestamp column, which generally is the time that your model made the inference, so made the prediction. We're going to have to specify a list of metrics. So we can use quite a few metrics. We can use ROC AUC, we can use F1, we can use precision. Let's keep to F1 here. And we're going to define a chunk size. So basically, how much do we want to aggregate data? So we're going to define it just like we would define a scikit-learn predictor. And then we're going to fit it again using the exact same kind of structure as scikit-learn uses. So it should be very easy to use. And then instead of predict, what we're doing is we're doing estimate. So we're fitting on reference, we are estimating on analysis. Then the second step is to just take a look at what actually has happened. So we're going to use very simple kind of pandas-based dot plot when we're going to plot performance, and we're looking at metric ROC AUC, and we want to see whether we want to plot reference, yes or no. And we see here that we have a very nice interactive visualization when we see per chunk, we see what is the performance in terms of ROC AUC on our reference time our reference data set and our analysis data set. So you can hover over it to see what is the actual chunk, when did it happen, and what is the actual performance. And it happens in time. And if there is a significant drop, so it drops out of, if I believe correctly, the default parameter that you can also change is 3 standard deviations from the reference performance, you will see that our model actually drops here and we have drift detected. So the performance has dropped significantly in the chunk from April the 30th to September the 1st, 2019. And then the performance has not improved ever since. So it means we would want to retrain our model at least, and if retraining does not help, then we would need to go deeper and do a manual analysis. And how we would do such an analysis? So then we would actually look at univariate data drift calculations first and foremost. Maybe there's something just very simple to figure out, very easy, very interpretable. So we're gonna look at for which columns we actually want to detect our univariate drift. So we're just gonna use the columns that are there, which is timestamp, predict proba period, and also model outputs. So let's define these columns that we're gonna detect the drift for. If you want to do it for everything, you could just take all. Here we're gonna exclude the timestamp. So we're gonna do reference.column. So we take all the columns and we're gonna exclude the timestamp. We're gonna exclude widespread probability, so the probabilities. We're gonna exclude period because of course it's something that's not related to the model. It's just some kind of metadata. We're gonna exclude the model predictions, the target, and the ID because ID is not a feature. And then we're gonna initialize again this object as before, and we're going to fit it, and we're gonna calculate drift. So again, we're using the same exact interface that scikit-learn uses. So we're taking univariate statistical calculator. It does what it says. We're gonna do this calculation for these features. We're gonna take the timestamp as the timestamp column and the chunk size, again, the chunk size as we defined it above. And we're gonna fit, and this time we're not estimating, we're simply calculating. So we're gonna say dot calculate. And let's take a look at it for every single feature. So we're gonna loop through all the features that are in feature column names. So you don't have to remember those. You'll just look at the object, and one of the properties of this object is just feature column names. So the features for which we actually calculated drift. And we're gonna plot it using kind of pandas or seaborn style interface. When we want to see the actual drift, we're gonna we're gonna look at the statistic as our metric, and we're gonna, of course, plot the reference as before. And then works quite fast because there is quite a lot of data actually. It's very fast. And we'll see that there is exactly in the time when we expected very strong drift, as our KS statistic goes from basically 0.01, so definitely not significant, to 0.45, so definitely very, very high metric. We're not, mind you, we're not plotting p-values here. We're plotting the statistic that you need to use that actually shows you the magnitude of the difference, and you will use it to calculate p-value. And if we see that drift is detected, it means that p-value is significant, it's above 0.05. And so we see that for salary range and distance from office features, we have drift. For gas price, there is no change, unlike in the real world. For some other features, we also have changed. So here we could take it and try to figure out what exactly happened based on our understanding of the domain and of the data set. Let's not do this analysis now, obviously. And as I already mentioned, we also have some kind of false positives here, where this is statistically significant, but actually from a machine learning monitoring perspective, this kind of drift is not persistent. It is significant, but does not affect performance. So you will always see these kind of false positives. And that's one of the things that you should be worried about when using univariate data drift. that not all kinds of data drift lead to drop in performance. Now what we could do is we could kind of do a simple ranker. Here we can just manually analyze everything, but we also have a kind of a mini feature when you could look at how many alerts you have, and maybe these are the features we should look at first. So you rank it by univariate results, and we'll see which of these features actually have the most alerts. And we can see whether we want to exclude everything that's not drifted, so take only drifting features or not. We're going to take all the features, and we see, for example, that gas per price and workday is the same, but all the other features actually had some kind of changes, and tenure is most likely a false positive. Now, as we already said, that we calculated that, let's see a bit more of how the statistical calculator works, this time not on the input features, but on the output. So we want to see now if there is so-called prediction drift. So we, as always, same kind of interface when we're looking at widespread proba, and we're just fitting those and then calculating those. Now we're gonna show the feature, and we'll see just one simple, similar by now, hopefully, plot when we see whether there is a change in the distribution of model outputs. And we see here that there is some small change, but as we already know, the most important plot is this one. There was some drop in performance, but it was not significant. It was still within kind of natural variance of the model. And we see here that there is a very strong change in how the widespread proba is distributed, so how the predicted probabilities are distributed. And last thing I want to show, which kind of concludes the quick start and how you can get started with NumML, is looking at the multivariate data drift. So we will perform data reconstruction with principal component analysis. And as always, we fit it. Maybe let's make it look nicer. We're gonna do it like that. So we, as always, have the feature columns, which one is the timestamp column, and we give the chunk size. And that part is going to take slightly longer to calculate as we need to transform the model. It's ready. And we're going to fit and calculate. And now let's quickly visualize it using the exact same interface as always. And we will look this time not at the statistic, but at the reconstruction. And here we again see that our false positives in the first and third month disappeared. So it's much more robust measure. And we see that there is a very significant increase in reconstruction drift in relative terms, just when all the other drift happened and just when the performance dropped. So let's maybe plot it again here just to see it in one screen, how one corresponds to the other. And you see basically that there is almost one-to-one correspondence between those two. And data reconstruction drift actually is a reliable prediction of the performance. So that's really it. Thanks for following and listening to me. And now let's have a second round of questions.
Q&A round 2. All right, so our first question, this is from Aaron. Have you encountered any other failure types besides label leakage, time leakage / drift, overfitting, and underfitting?
Besides those three, you mean?
Yeah.
Okay. So yeah, the things that Aaron mentioned are really related to model development. So you have data leakage when you do not correctly split the data and you do some kind of transformation that also includes the test set, etc., etc. Here, what we're focusing on is really inherent changes in the underlying data that cause the model to not perform well. So in that case, you could see data drift as failure itself, concept drift as failure itself. Another kind of interesting failure that can happen is what I mentioned, these feedback cycles, when actually what you do impacts real world, and that actually means that the population itself changes.
Mhm.
I'm going to give you another example here. It has to do with churn detection. Imagine you're trying to do churn, and you're working with a company with very low churn and very stable customer set. Then, as you stop the most customers that they are most likely to churn, your model, and you exclude them from the data set because they're not churning or they will not churn for the next 6 months or whatever is the business rule, your distribution of your data will actually become that there is less churners, which means that your confusion matrix will change, which means that even though the model is actually performing just fine, your performance metrics will most likely go to shit, because the people who are very easy to predict that they will churn, they are no longer in the data set because they either already did churn or they were stopped from churning. Which means that you will see failure, but actually the model is not failing from business perspective. It's only failing from technical perspective. That's why monitoring plus very deep, like under business understanding, is really important in kind of post-deployment data science.
Okay. And then this is from Amit. Amit is on one of our live streams. Can a chatbot be made self-learning using continual learning technique?
I'm not sure how relevant that is to anything here. I mean, you could, but why? Like, there is just so much more data that's available elsewhere, and these, I don't know, a few hundred pages of conversations you will have will not improve the chatbot much. So
seems like a bit of an overkill.
Yeah, like, you can, but why?
Okay, so that's all the questions I'm seeing on my end. So Voyatech, thank you for joining today. I'm just going to share my screen really quick because we have a couple of events next week, and I want to make sure that everyone is aware of those. So the first one we'll be having is July 19th, and this will be happening at noon Pacific time. So we're going back to kind of the regular time that we normally host these community events. This is going to be designing your organization for AI and analytics success. So if you're a team manager out there, or if you're running your own company, or maybe Voyatech, I'm not sure if you would need to join this, but someone like yourself, this might be good for you to join. This is going to be Scott Burke. He's the founder of It's All Analytics, and he's also written 4 books on AI, data science, and analytics. And this includes it's the series It's All Analytics. So we hope to see you there. You can RSVP on our website, or also join us on one of our live streams. I think we'll have an event on LinkedIn that you can sign up on, as well as Facebook, and then you can also just subscribe to our YouTube channel. It'll be there as well. And then on July 20th, the next day at 10 a.m., so the same time as today, we have an introduction to convolutional neural networks with TensorFlow. And this is going to be given to us by Neil Leiser. And Neil is a data scientist at, I'm actually not sure how to pronounce his company's name, so I'm just going to assume its initials and say IWOCA. And so he's a data scientist at this fintech startup. So he's going to be using TensorFlow to give us this introduction on neural nets. So hopefully we'll see you all at one or both of these events. Voyatech, thank you so much for being here today. We'll make sure to get your recording up, and with the links that you shared with us in, whether it's the description, like on YouTube, it'll be in this description. If it's on our website, it'll be under our resources tab, and we'll share that with you via email, as well as everybody else who RSVP'd. We'll share the video with you via email as
Thanks
well. So thank you so much. And everyone, I know it's early on my side, but Voyatech, I think it's getting fairly late in the day. It's probably early evening for you. So I hope you have a good evening. 7 p.m. Okay, so I hope you have a good evening, and everyone else have a good rest of your day.